Okay, let's get started. So, okay, before I start, how do you all find the new quiz type? Do you like it? It's like multiple choice and like true false. So if you like it, I might start moving to that. So how do you all like this new quiz format? Like the one on Canvas, I guess. I mean, assuming those who took it, so pretty sure it's not due yet. But oh wait, no, did I assigned it to start on Tuesday, right? All right, I'll ask on Thursday. I forgot. I didn't go over Cauchy sequences yet. Okay, so a sequence. So let's go over Cauchy sequences. So a sequence Sn is Cauchy. If and only if for all epsilon bigger than 0, there exists a number. Yeah. So here, since the book doesn't require n to be natural, but do be careful that most other books require capital N to be a natural number. For this is bad. For m n bigger than n, it's running out of battery. Sn minus Sm is less than epsilon. So, and then we have that a sequence, sorry, you have to bear with me. A sequence is convergent if and only if it is Cauchy. So really quickly, why do we care that if a sequence converges if and only if it's Cauchy? Why do we care about this new definition, right? Why not study just, I guess, just the original definition of convergence? Why is Cauchy better? Does anyone know? Because if it's the same, you might ask why do we even study this, right? So, any ideas? Let me get my charger really quickly. Anyone? It's more general. Okay. So if we look at the definition right now, what do you notice? Like, what's the difference? I guess in the past, instead of that SM, we had like S, right? So what you're going to notice is in the past, all the limits you've been doing had you had to know what the limit was, right? So if you didn't know what the limit was, it just doesn't work, right? So okay, so now what we're going to see is, so again, in the past, so let me ooh, this is bad. Okay, hopefully this is better. Please work. Okay, this is not good. So give me a moment. So, okay, Apple Pencil connected. Okay, it's at 47%. Technical difficulties. So, again, great. So, Cauchy, right? Don't need to know what the limit is. Know what limit is. So again, right? Like in the past, right? Like limit, please work. Limit n goes to infinity, 1 over n. You had to know it was 0, right? If you didn't know it was 0, you couldn't do the epsilon definition, right? In the past. But Cauchy, you don't need to know what the limit is, right? It will, because all the terms here just involve your sequence. So that's the advantage of Cauchy. But on the other hand, right? On the other hand, if you prove, you know, sequence is Cauchy, you just get it converges, right? It won't really tell you the limit unless you do more work. So that's the reason, you know, there are advantages, right? So advantages and disadvantages. Okay. Any questions so far? If not, we will move to problem sets, because that's pretty much the new thing. So let me do 10.9 because your homework 10.10 is pretty much the same. So let's do 10.9. So 10.9 says S1 is 1 and Sn plus 1 is n over n plus 1 Sn squared. Yeah, so sorry for my Apple Pencil being out of battery. For n bigger than or equal to 1. So and remember in the past, we could answer this question, right? So like if limit existed, what would it be, right? It would be limit n goes to infinity, Sn plus 1. Let me erase this. Limit n goes to infinity, n over n plus 1. Now, n over n plus 1, it goes to 1, right? So this, if the limit existed, say the limit went to, say limit is s, then what we have is, okay, this thing goes to s, and this thing goes to s squared, right? So you either had, you know, s squared minus s is 0, so s is 0 or 1, right? Or but now we can actually do better. So in fact, we could have done better last section, but last discussion. So how do I show the limit actually exists? So the hard way would be, in this case, to show as Cauchy. But is there an easier way? Does anyone know? So let's sort of, you know, examine this question. So how does this thing behave? Well, what we're going to notice is this thing's decreasing, right? Because if you just write out the first few terms, so let me just first show that if you look, it's sort of decreasing because you're multiplying by n over n plus 1, which is smaller than 1. And what do we know about decreasing sequences, or i.e. monotone sequences? So monotone sequences, there's 3 cases, right? If it's bounded, it converges, right? You had a theorem, bounded monotonic sequences converge. Or it's unbounded, and it goes to positive infinity or negative infinity. So I mean, in this case, it's decreasing, so it will go to negative infinity if it's not bounded. So all we have to do is show that it's decreasing and bounded, right? And then we use the theorem that bounded monotonic sequences converge. And that's pretty much the same thing on your homework, I think 10.10, if that was your homework question, because I think someone asked me on it. So you see part C is you show it's decreasing, right? And then part D, to show a limit exists, you show you're bounded, right? If you're bounded and you're decreasing, i.e. monotonic, you converge. So really quickly, it's from last section, but let me just quickly show you that theorem. Almost there. Right here, yeah, theorem 10.2, all bounded monotonic sequences converge. So, okay, we go back to the question set. So what we're going to do is we're going to show it's bounded, right? So let me go back here. So we have this, right? S1 is 1 and Sn plus 1 is this, right? So again, given S1 equals 1, what is S2? So S2 is a half, right? Because if you plug in n equals 1, it's 1 over 1 plus 1. And then S1 squared, right? So again, 1 over 1 plus 1, S1 squared. But S1 is 1. So this thing is a half, which is less than 1, right? So again, you do, assume Sk less than 1, then Sk plus 1. No, whenever you do this, it's always induction, right? So since Sk is less than 1, Sk squared is less than 1, so this is less than or equal to k over k plus 1 times 1 squared, which is less than 1, right? Because k over k plus 1 is less than 1. So you get by induction, some short induction. Sk is less than 1 for all. I guess I guess less than or equal to, because S1 was 1 for all k, right? So we're bounded above, right? And hopefully it's clear that, Sk plus 1 is k over k plus 1 squared Sk. Or, sorry. So Sk squared. Now, this thing's bigger than or equal to 0, right? Because when you square something, it's bigger than or equal to 0. And k is a natural number, right? So we certainly have that it's positive. And please, okay. And S1 is 1, right? So, which is bigger than 0. So we're bounded above and below, right? So we are bounded. So this is a bounded sequence. And how do we check it's decreasing? Well, let k be an n. Then again, Sk plus 1 is k over k plus 1 Sk squared. So here, since we proved Sk was smaller than or equal to 1, this thing is certainly smaller than or equal to. So let me just write equal first, and then let me write equal first. So Sk times Sk, right? Sk squared is just that. Now, Sk is smaller than or equal to 1. So this is less than, and k over k plus 1 is smaller than or equal to 1. So we certainly have this, right? And that certainly shows we're decreasing, right? So this term's smaller than 1, this term's smaller than or equal to 1 from like here, right? So we have that it's decreasing. So Sk bounded decreasing sequence So SK converges, right? So we basically show part B of 10.9, right? And how do you show it 0? So you can actually show this is strict, right? In fact, this thing is strict because k over k plus 1 is strictly smaller than 1. So if it's strict, so as you know, S1 is 1. S1 is 1, and SK is smaller than, you know, we certainly have that it's and SK decreasing strictly, so less than, not less than or equal to. The limit can't be 1, right? So I trust you can all show that. So you're decreasing and your first term is 1. And we showed above that either our limit is 1 or 0, right? So you only have one other option, and that's 0, right? So limit is 0. Yeah, everyone good so far? Yeah, so in general, if you want to show a sequence converges, right, you have like 3 options, right? You either know the limit, what the limit is, and then you use the epsilon delta definition to show what it converges to. Second is, I mean, most of the case, if you're given a recursive sequence, you're going to be showing it's bounded monotonic. But third, if you, another way would be to show the sequence is Cauchy, right? I wouldn't, so if you look at it, you would have to do Sn minus Sm, right? And you can write Sn, Sm in terms of Sn using this recursive relation, and then you'll get the same result, right? So another way would be to show the sequence Cauchy. I wouldn't advise it. I feel, you know, showing decreasing bounded is easier in this case, but yeah. Okay. Any questions so far? Okay, so let's do 10.7. So S be bounded non-empty subset of R such that sup S is not an S. Prove that there is a sequence Sn of points such that limit Sn is sup S. So this is actually not that hard. So 10.7, S bounded non-empty subset of R, and sup S is not an S, right? Because if sup S was an S, this doesn't really matter, but if sup S was an S, you just take your sequence to be the sequence, the constant sequence, sup S. So S1 is sup S, S2 is sup S, S3 is sup S. So it's trivial. So they didn't really, you know, include that. Okay, so again, so let me remind you that, you know, show there exists sequence Sn such that Sn goes to sup S. So, okay, so how are we going to do this? So you could choose anything that goes to 0. I'm just going to choose 1 over 2 to the n, right? This goes to 0, right? So the first step would be, here's sup S. Look at the ball. I just care about this side because sup S is the biggest. So this is sup S minus a half. And this is, you know, sup S plus a half. Now, on this ball, there has to be a point here, a element in S. So why? If there was no elements in S, in that interval from sup s minus a half to sup s, this thing will be my new, if not, sup s minus a half is new upper bound, right? So, please. Okay, upper bound. Right, you have to have a point there. If not, I mean, we get a contradiction, right? Because we get a new upper bound, and sup s was the least upper bound. And so we get, so again, from here, we get, please, we get, please. Okay, this is not good. So let me, what am I? I'm still at 46%. Okay. Okay, I'm gonna do something different maybe. So let me, just for this class, sorry about this, but I will maybe write on line paper, if that's okay. So how am I gonna do this? So, okay, sorry about this, but this will have to do. I think my Apple Pencil is running out of battery. So can everyone see this, like me writing? So let me go. Okay, great. Impromptu. This has never happened. I'll make sure I charge my pencil next time. So here, what we have is, okay, we have on this interval, so we get S1 in S in this interval, right? In sup S minus a half and sup S, right? So we all agree with this. Now we do the same thing, right? So now consider 1/4. So now we consider this interval. So sup S is here, and I go from sup S minus a fourth, sup S plus a fourth. And again, same argument, there has to be a point here, right? Or else sup S minus a fourth is the new upper bound, right? So there exists S2 such that in S such that S2 is in sup S minus a fourth sup S. And here, right, we hopefully you all know how to continue, right? So from here, we will get that, okay, there exists Sn such that Sn is in sup S minus 1/2 to the n. So remember, when S2 is 1/2 squared, right, which is a fourth, and S1 is 1/2 to the first, right? So this matches. And we get this, right? And this is your sequence, right? Because 1/2 to the n goes to 0. So your sequence certainly approaches sup S. So now what I'm claiming is here is easy because Sn need not be, they didn't ask for this, but Sn need not be increasing. Yeah. Right, so here what we're going to get is, we can actually make this increasing if you like. So let me just show you how. So let's go back to S1. We assume we had S1, right? Or S1. Now we consider instead this sequence. So so instead of a fourth, I let the, I take sort of like, because the point is, if you look at this, right, S2 could be still, how do I say this, right? If I chose a S1, let's say sup S minus a half, this is sup S minus a fourth, and this is sup S, right? So what does the S1 here? S1 just needs to be in sup S minus a half to sup S, right? So it could be here, in which case it's nice, but it could be here, right? We could have chosen the point, that this to be our S1. Because if you notice above, it just needs to be like right here, right? Sup S minus a half to sup S. So, but now when we choose S2, our S2 just needs to be in sup S minus a fourth to sup S, right? So our S2 could be here, right? And that's still certainly valid, right? So it could be like our S1 was like here, and S2 was like here, right? So sorry it's moving because I'm like holding the iPad with like one hand. So what you're going to see is, how do we make this increasing? Well, instead of a fourth, we consider minimum of, how do I want to say this? So minimum of sup S minus S1, I guess, and sup S minus 4, right? So right? So instead of taking this interval now, right, we take this one, right? We take this interval, and then we find our S2, right? Then find S2, and then so on and so forth, right? So for S3, you take minimum sup S minus S2 and sup S minus a 4, right? So in this way, you can make it increasing. But the problem didn't really say that. So the problem just wanted, just wanted a sequence of points going to sup S. But if a harder question would be to make it increasing, and you could do that just by what I just wrote. Okay, any questions so far? Let me go. Okay, so let me just do one more since it's not really that. Okay, so let's start. So let's do one more. So the one I'm going to be doing is pretty important. So it's 10.6. So we haven't really gone over sums yet, but let me just give a quick review. Does everyone know that, from Math 2B, this thing converges, right? It's a geometric series, right? So what you're going to notice is, for convergent sequences, what is the sum, right? It's this infinite part, just saying this, right, goes to, right, by definition, when the infinite part is just the limit of this, right, when n goes to infinity. So what you're going to see is, okay, if we use the limit definition, it's saying for n, bigger than equal to capital N, this thing is small, right? The limit minus my sequence. right? And what is this thing? This thing is just like, we call this the tail. So, you know, right? This is just, you know, you're summing from n equals 1 to n, and then n equals 1 to infinity. Well, what are the terms that remain? Well, the n plus 1 term to infinity, right? So basically, you can make the tail small. And that's the idea about Cauchy sequences. So we have that. So let me go back to the question. So we're going to be using the fact that things are sums, right? So so from here, it's going to be like, we have how we need to prove it's Cauchy, right? So let's let epsilon be bigger than 0. Want to show, you know, there exists n such that for m n bigger than n. So this will be our first Cauchy problem. Sn minus Sm is less than epsilon, right? So again, without loss of generality, we could assume n bigger than m, right? I mean, one of them has to be bigger than the other. I mean, if they were both the same, then Sn minus Sm is 0, right? So we might as well just assume, you know, n is the bigger one. So in which case, what we're going to do is we're going to use triangle inequality many times. So we have, so again, we have that Sn minus Sn minus, let me just write Sk minus Sk minus 1 is smaller than what was the assumption? So the assumption was it's smaller than 2 to the negative k, right? So this is smaller than 2 to the negative k. So what we're going to do is we are going to choose n. So some, you know, we can make the tail small, right? So some n equals, you know, n to infinity, 1 over 2 to the n is less than epsilon, right? So this was what I was talking about in the beginning. I mean, in this case, just replace n with like n minus 1. But so here we could choose n such that this is true, right? This thing is certainly smaller than epsilon, right? So from here, we are pretty much done, because we're going to get this. So I'm going to subtract n minus 1, but add n minus 1, subtract Sn minus 2 plus Sn minus 2. And I'm going to go all the way to plus Sm plus 1 minus Sm. Right? So no, I didn't change anything, right? I only added and subtracted terms. And why do I do this? It's because this thing over here only relates like one term and the next one, right? So the k minus 1 term, the kth term. I don't know how the mth term, and the nth term relates, but I can certainly just keep scaling it by 1. And by triangle inequality, I get this. Right, so Sn minus 1 minus Sn minus 2, all the way to this, right? Everyone clear? So I use triangle inequality many, many times. Now this is less than or equal to what? 2 to the negative n minus 1, right? Plus 2 to the negative n minus 2, all the way to 2 to the negative m, right? Everyone clear? So I'm using, you know, I'm using this part to replace everything with 2 to the negative power. Okay, but this is just equal to what? this is just sum k equals m to, I guess, n minus 1, 1 over 2 to the k, right? So again, the negative sign, I could bring it down, right? Like 2 to the negative 1 is just 1/2, right? So I can get rid of all those negative signs in front of my thing by pulling it down. And certainly, this is smaller than or equal to, since m is bigger than capital N right here. So if you look right here, m is bigger than or equal to capital N. This is smaller than me just adding, starting at k equals n, right? And this is certainly smaller than me going to infinity. Right? I'm just putting more terms in my sum, right? If I do that, I certainly make it bigger because 1 over 2 to the k is always positive. And this was less than epsilon, right? This is exactly this thing. I mean, n is like a dummy variable here, right? So this thing is smaller than epsilon. So we've shown it's Cauchy by using triangle inequality like many, many times. So, so let me go to, I'll conclude the first question. So here we've shown it's Cauchy, right? Using triangle. So the second one, why does it fail for 1 over n? Well, for 1 over n, we certainly have this, right? For 1 over n, why did this matter? Why did we consider 1 over 2 to the k? It was because this thing converged, right? So, but what do we know about this? I do 1 over k. This thing diverges, right? It's harmonic series. Agree? So what you're going to see is you can repeat the whole proof with any convergent series, right? There was nothing special about this 1 over 2 to the n. It was just that because the sum converged. You could have done this with 1 over 3 to the n. The same proof would work. The only reason we can't do it for 1 over k is because the sum 1 over k diverges, right? So that's sort of a trick for Cauchy sequences. If you know you have a bound on like a term in the next one, then you use like triangle inequality many times. Yeah. So everyone good? So I'll stop there. What? I mean, I don't know what you're referring to, but yeah. Okay. So since I mean, that's actually all I have for today. So on next time we'll go over subsequences, right? And then I'm pretty sure that's what your midterm should cover up to. But yeah. Okay. Any questions? All right. Great. Thanks.
I have a
Yes.
question.